So until now, we have covered lots of it. Now this is the end of processor fundamentals. This might be the last lecture, or maybe we may have another lecture. So let's revise a little before we go any further. We have covered until assembly language programming. So let's have a few key terms first discussed again, just to revise. Key terms for assembly language. So the first term is machine code. I hope that until now, whatever that we have discussed, you would have understanding of these terms already. Let's just revise them. First one is machine code. Machine code, the programming language that the CPU uses. It is in the binary form. Then instruction. Instruction, a single operation performed by the CPU in the machine form. A single instruction, a single operations performed by a CPU in binary form. Assembly language. Assembly language is a low-level machine-specific programming language that uses mnemonics. All the opcodes that we have discussed, LDD, LDI, LDM, they were all mnemonics. And then what we have, opcode. It is a short of operation code. What it is? It is a short of operation code. The part of a machine code instruction that identifies the actions CPU will perform, the opcode. And then the next part of the instruction, that is operand. Operand is the part of a machine code instruction that identifies the data to be used by the CPU, either directly from the register or the memory or the value. Then we have got assembler. We will talk today especially with respect to assembler. Assembler, like compilers and interpreters for assembly language, the translator program which translates from the assembly language that we write to its machine equivalent code in binary is called assembler. It is a computer program that translates programming code written in assembly language into machine code. Assemblers can be one pass or two pass. This is what we are going to discuss today. Assemblers are of two types, one pass or two pass. Then we have next term, which is instruction set. Instruction set. So instruction set, the complete set of machine code instructions used by the CPU. If you do remember, there were groups and the instruction sets were falling in those groups. Input output group, memory handling group, and others. So all the commands that we have seen until now, they are combinedly call what? Instruction set. What do we call them? Instruction set. It's a revision bit and the preparation towards the end of the topic. And then we have got object code. This might be a new term for you, object code. A computer program after translation into machine code. Okay, so whatever the program that we write, when translators like compiler, interpreter, and assembler, when they turn our written program into machine code form, it is said to be the object code. And then we have got addressing modes. Addressing modes. Different methods of using the operand part of a machine code instruction as a memory address. This is LDD, LDI, LDM, LDR, LDX. These are what? Addressing modes. Different methods of using the operand part of a machine code instruction such as memory addresses. Then we have got absolute addressing. Absolute addressing. Mode of addressing in which the contents of the memory location in the operand are used. Absolute addressing. Whatever the address that you have given will be reached out directly in the RAM and the content will be accessed and brought into what? Accumulator. Absolute address. Mode of addressing in which the contents of the memory location in the operand are used. And there is this direct addressing. Mode of addressing in which the content of the memory location in the operand are used, which is same as absolute addressing. So absolute addressing or the direct addressing are basically synonyms. Indirect addressing. Indirect addressing is a mode of addressing in which the content of the contents of the memory location in the operand are used. In which the contents of the memory location, in which the contents of the content of the memory location in the operand are used. Means the address that is given is not the address of the data that we require, but it is the address of the data. We have discussed it, we have solved past paper questions related to it, so you should have a better idea of it now. Then we have got indexed address. It is a mode of addressing in which the contents of the memory location found by adding the contents of the index register to the address of the memory location in operand are used. So the base address is added to the offset and the final address is found. So whatever the address that is given in front of LDX will be added to the content of what? The index register, which is base, offset, and the final result is found. Then we have got what? Immediate. Immediate addressing. immediate address. Immediate addressing is what? We have not given any address, but the value itself, and we use that hash sign. It is a mode of addressing in which the value of the operand is used. Value of the operand only is used. All right, so no addresses. Then, if you do remember, there was one thing that we discussed one day was relative addressing. So, mode of addressing in which the memory address is used is the current memory address added to the operand. So, what is relative addressing? Let's say you want to go from current memory location 5 places ahead. So we will be using an addressing mode that is relative to the start of the program or the current location. And we have seen this register BR, base register, which holds the address of current program being executed. The first address, base register, holds the address of the first instruction of the current program which is being executed at the moment, and relative to that address we go further. That is called relative addressing. And then we have got symbolic addressing. So symbolic addressing, in today's lecture we will be discussing symbolic addressing especially. So today we are going to discuss assembler types and symbolic addressing especially. So what is symbolic addressing? It's like the use of variable. It's like use of the variables in modern languages and subjects. So instead of absolute addresses, what do? We use representations, which are called symbols in assembly language. So symbolic addressing is the mode of addressing used in assembly language programming where a label is used instead of the value. So we may call it label, we may call it symbol. So let's have a discussion of assembly language and machine code first, so that we could go ahead with our topic today. Our topic is especially this part, show understanding of the relationship between assembly language and machine code, and describe the different stages of assembly process for a 2-pass assembler. And for 2-pass assembler, apply the 2-pass assembler process to a given simple assembly language program. Afterwards, tracing these following groups: data movement group, input output, arithmetic, conditional, unconditional jumps, compare statements, mode of addressing, that we have already covered in our previous lectures. Today, we are going to cover these 2 topics: relationship between assembly language and machine code, and describe the different stages of the assembly process for a 2-pass assembler. So let's first discuss, show understanding of the relationship between assembly language and machine code. So assembly language and machine code. The only programming language that CPU can use is machine code. Every different type of computer or chip has its own set of machine code instructions. A computer program stored in main memory is a series of machine code instructions that the CPU can automatically carry out during the fetch, decode, execute cycle. Each machine code instruction performs one simple task. For example, storing a value in a memory location at a specified address. Machine code is binary form. It is sometimes displayed on a screen as hexadecimal so that human programmers can understand machine code instruction more easily. So whenever we write in assembly language. Assembler turns that assembly language into machine code. Machine code is in binary form. So programmers, as you would have seen, that the use of hexadecimal numbers, use of hexadecimal number relatively makes it easy for the programmers to observe the binary code. So machine code is in binary. It is sometimes displayed on the screen as hexadecimal so that human programmers can understand machine code instructions more easily. Writing programs in machine code is a specialized task that is very time consuming, as you would have idea from the previous lectures that it is really time consuming, and often it is error prone, as the only way to test a program written in machine code is to run it and see what happens. In order to shorten the development time for writing computer programs, other programming languages were developed. So instead of making programs in machine languages, we now use other programming languages. Instead of assembly, we use high-level languages. Instead of low-level, we use high-level languages where the instructions were easier to learn and understand, as in pseudocode or Visual Basic or Python or Pascal. Any program not written in machine code needs to be translated before the CPU can carry out the instructions. So language translators were developed, like compilers and assemblers. The first programming language to be developed was the assembly language. Initially, when nothing was there, everything used to be in machine code. Machine code was actually in binary form, so it was not easy to handle everything in binary form. So they developed assembly language first. So whatever that we have studied in our previous lecture was assembly language. This is closely related to machine code. Now, what is the topic? The relationship between assembly language and machine code. If you do remember, we did a question where every opcode had its own binary. So in binary form, it is called machine code, and in the human readable form, it is called opcode, mnemonic, or assembly language instruction. So what is the work of assembler? Assembler takes that assembly language instruction and turns it to its equivalent binary form. So that is actually the work of translator. So if it is a language which is not assembly, it is a language like pseudocode. If it is a language like Visual Basic, Python, Pascal, it is high level language which is easier for humans. So what they have done, they have invented compilers and interpreters. Compilers and interpreters. So compiler and interpreter are used to turn that high level language programs into the machine code. The first programming language to be developed was assembly language. This is closely related to machine code and uses mnemonics instead of binary form. All right. So let's say what we are studying now, the relationship between assembly language and machine code. Relationship between assembly language and machine code. Relationship between assembly language and machine code. So let's say in assembly it is written LDD and load directly from a label called total. So instead of direct address, we used what? Total. Let's say LDD's machine code in hexadecimal is 01. It is hexadecimal, hex. It is machine code, but it is in hex. So what is this? This is assembly. Assembly instruction. This is hex. Let's say for total, it is 40. If it is in binary form, machine code would be what? It would be, let's say if it is 1 byte, then it is 1. 1, 2, 3, 4, 5, 6, 7, 8, 1. And then let's say it goes further. Let's say 1, 2, 4, 8, 16, 32, 64, 128. This is what? 40. So you can see these two are actually machine code. What are these two? These two are actually machine code, and this one is assembly language. What is this? Assembly language instruction. So from this assembly language instruction, assemblers translate it to machine code. So it is in binary form. And when it is shown over the screen, you may choose to have it in the hex form. So this is the difference between machine code and assembly language. So what is the relationship? The relationship is 1 to 1. The relationship is 1 to 1, means for every assembly language instruction, there is an equivalent machine language instruction. Whenever there is one assembly language instruction, there is an equivalent machine language instruction. All right, so what is the relationship? 1 to 1. All right. So the structure of assembly language and machine code instruction is the same. Each instruction has an opcode. This is opcode. This is opcode. This is opcode. That identifies the operation to be carried out, like LDD over here by the CPU. Most instructions also have an operand. So this is operand, this is operand, this is operand. That identifies the data to be used by the opcode. All right, so this LDD is actually what? This LDD is what? This is opcode. This total is what? Operand. Opcode. Operand. This is opcode and this is operand. Okay, so that is how it works. Now, stages of assembly language. So what is the relationship between assembly language and machine code? Their form, their shape, but there is always one machine code instruction for one assembly language instruction. The relationship is 1 to 1. Now, stages of assembly. stages of assembly. That is how the code is basically assembled. Before a program written in assembly language source code, whatever the codes that we have traced were in assembly language because they were not in hexa or binary, so we cannot say that they were in machine code. They were in assembly language. And the code that you have seen, like one of the instruction over here on the screen, the LDD total, they are basically called what? Source code. Before program written in assembly language source code, all right, before program written in assembly language source code can be executed, it needs to be translated into machine code. The translation is performed by a program called assembler. So the source code requires to be converted with the help of assembler into machine code form. An assembler translates each assembly language instruction into machine code instruction. An assembler also checks the syntax of the assembly language program to ensure that only opcodes from the appropriate machine code instruction set are used. This speeds up the development time, as some errors are identified during the translation before the program is executed. So assembler helps us to make our program good. There are two types of assemblers: single pass assemblers types of assemblers. Single pass and two pass. Single pass assemblers and two pass assemblers. Single pass assemblers and two pass assemblers. A single pass assemblers put the machine code instruction straight into the computer memory to be executed. A single pass assembler puts the machine code instructions straight into the computer memory to be executed. A two pass assembler produces an object code program in the machine code that can be stored, loaded, and executed at later stage. So a single pass, what it does, it just takes the program and put it in the computer's memory to be executed. A two pass assembler, this is the part of the syllabus, two pass assembler. The single pass is not the part of the syllabus. Let me revise. A single pass assembler puts the machine code instructions straight into the computer memory to be executed. So it takes this machine code and put it in memory to be executed. Obviously, when we write a program, the program is, the assembler takes the machine code and puts it in the memory directly. Whereas the two pass assembler produces an object program in machine code that can be stored, then loaded and executed at later stage. This requires the use of another program called a loader. So two pass assembler requires loader. What does it require? Loader. Two pass assembler needs to scan the source program twice. So they can replace labels in assembly language with memory addresses in the machine code program. There are past paper questions which require you to do the work of two pass assembler. So pay attention to it. So let's take the same instruction once again. Let's see how it works. So the instruction is LDD total. So system in pass 1, what it would do, we are studying 2-pass assembler now. In pass 1, what will happen? Assembler will read the assembly language program one line at a time. Number 2, ignore anything not required. What is not required? Like comments, we don't need them when we are converting to machine code. Then it allocates memory addresses for the line of code. So it reads one line at a time and put that at one memory location. Check the opcode. Checks the opcode in the instruction set. So we have got a collection of instruction. It checks that that opcode is there or not. Add any new label. Add the label. New one means which is not yet found. It's a new one in the table. It maintains a table which is called symbol table. It maintains all the labels in that table. I will tell you that how the table is made. It is called symbol table. And then that label is also basically pointing out to a data location in the memory. So that table is updated. So what it does, the assembler places address of the label in the symbol table. All right, so it takes one instruction at a time. If it is comment or anything which requires to be ignored, it ignores it. Then it finds a memory location, places that instruction in that particular memory location, checks the opcode of that instruction. If it is correct, it is in the instruction set. If that instruction has a label in it, like over here we have got a label called total, then that label name is added to a table so that it could refer to it afterwards. Obviously, if it is total, it means it has some data like over here. It has some data like over here. Okay. So that label is actually in the memory. And if it is in the memory, there would be an associated address. That address is updated into the symbol table. This is pass 1. You would have to actually remember this. Then we have got pass 2. So pass 2, what it does, it reads the assembly language program again one line at a time. In pass 2, the assembler reads the assembly language program one line at a time. Okay. Then what it does with that one line, it generates the object code. It generates the object code. What is the object code? We just discussed that. Object code is a computer program after translation into machine code. That generation of the object code is also including opcode and operand both. Opcode and operand from the symbol table that we have, from the symbol table that we have generated, or it has generated in one pass, in pass 1. And the last thing, it then saves or execute the program. It then saves or execute the program. So let me revise. There are two types of assemblers, single pass assembler and two pass assembler. A single pass assembler puts the machine code instruction straight into computer's memory to be executed. A two-pass assembler produces an object program in machine code that can be stored, loaded, and then executed at a later stage. This requires the use of another computer program called what? Loader. So loader is required to load the program and do all the things. Two-pass assembler need to scan the source program twice, which is called passes, so they can replace labels in the assembly program with memory address in the machine code program. So in pass 1, it reads the assembly language program one line at a time, ignores anything not required such as comments, allocate a memory address for the line of code that was just read, checks the opcode in the instruction set if it is found and if it is correct, add any new label to the symbol table with the addresses if known, place addresses of the labeled instructions in the symbol table. All right. Place addresses of labeled instruction in the symbol table. Then pass 2. It reads the assembly language program one line at a time. So this is the assembler which is reading the program once again, and it generates the object code including opcode and operand from the symbol table generated in pass 1, and then save or execute the program. The second pass is required as some labels may be referred to before their address is known. For example, let's write a program, and then we will, if we find time today or in the next lecture, we will solve a past paper question as well. Let's make a program, a source code program. Let's say this is label. This is opcode, and this is operand. Instead of absolute or direct addresses, we will use what? Labels. Labels. So LDD operand is, let's say, 200. Let's say we have got compare with 0. Then let's say we wanted to jump unconditionally at a label called what? Let's say let's call it come here. So let's say this is a label. How do we know this is a label? Because it comes before the opcode and it has got a colon before it. And let's make this operand a label, means come here. So get the idea. So instead of having over here, we used an absolute address. So system will load from the address 200. But in the program, this is an instruction, and this instruction is labeled. So whatever the address of this instruction is actually in the form of label, which we call a variable sometimes, or symbol sometimes. So this would actually make it jump to this instruction. So this program will go on and on and on. All right. So that is how, let's say I wanted to jump later. Let's say if the comparison was true, jump if equal, or JPE. JPE. I wanted to go to a location that is called found, or found here. Let's say that is here, found here. This is a label, so we put colon in front of it. And then what do we say? End. So what exactly happened? That whenever system or assembler finds a labeled instruction, this instruction has got a label in operand, it looks into the symbol table. Okay, it looks into the symbol table and then go there. Now let's say these instruction has got these addresses. This is 100, this is 101, this is 102, this is 103, this is 104. So it means label come here is at the address 100 in the memory, and label found here is at the address 104 in the memory. So what has changed? Just these labels. Just these labels. So this instruction is actually at this label, which is at address 100. So we can replace this come here with 100. So that would jump to 100. We can replace this, sorry, come here, yes, at 100, and found here is actually 104. So we can replace this found here with 104. That would be the same thing. But instead of using absolute addresses, what we have used? Symbolic addressing. So these are symbols or labels. So system has to have a separate table, which we call symbol table. That tables maintain label and its address, so that when the system is executing the program, it knows which label has what address. So the first label is come here. It is at address 100, and the second one is found here. Its address is 104. So this is called what? Symbol table. Okay. So let me revise. The second pass of the assembler requires, as some symbols may be referred to before their addresses are known. For example, over here, come here is forward reference for the JMP instruction. Forward reference means we actually will use this label later. Okay, so what will basically happen? Let's see, what is forward referencing and backward referencing? So let's say you are assembler, you are reading this line first. So this instruction is at the address 100, and you have seen there is a label here which we have not yet used. So this label will be taken and that will be placed in symbol table, and its address will also be placed in symbol table. When system will come over here, it will see that come here is used. So this is backward referencing because you are going back, and that particular symbol or particular label has already been listed in symbol table. So this is backward referencing. But over here, when we reach at the instruction JPE, which is at the address 103, it has got another label which has not yet been encountered by the assembler. It is not yet been encountered. Means it will only put the name of the label in the symbol table, but where it is found, system does not know because it will come later. This is called forward referencing. So system will put this found here over here, and when it will reach to the instruction where the label found here is put, it will take the address and put in the symbol table. All right. So that's about it for today. We will discuss this particular same two-pass assembler thing tomorrow once again. Okay, so that we could continue with the topic, and we will solve related past paper questions as well. Thank you very much. If there is any question, please do ask it.